Greg, are we waiting for someone or?
Excuse me. No, it's 8 a.m. We're ready to start, and I'm recording.
Okay, all right. Hello, everyone. So today we are going to cover the advanced set of AC analysis, transient analysis, something about noise analysis, and overview something about pole zero analysis. And today it's going to be more of a less of a demo time and more of a question and answer kind of a review. So I'll just go ahead and start with the parametric AC analysis. So this is basically parametric AC analysis. It follows the same structure as DC analysis. I mean, the only difference is that you're running the inner sweep as an AC sweep. You have your start frequency defined, your stop frequency. You have AC sweep type, which is either decades or like in octaves, or if you want a linear plot, you can say LIN. And then finally you have these AC sweep points, which the usual pick is 20 points per decade. As far as linear points are concerned, if you're sweeping your AC analysis linearly, you're defining the interval between two frequencies in terms of linear scale. Next, we have the parametric sweep or outer loop. So the parametric sweep at this moment helps a designer to vary the width and length of active devices. And you've got the device name, the device width, the start, stop, and step values for the parametric sweep. And we have the usual support for sweeping multiple devices at the same time. So you can say M1 width and then say M2, M3, M4. So it will concurrently sweep widths of all four devices at the same time. And this is the output field. Now, the output field at this moment is going to plot just the node, the output, a given node of your design. And this is quite usual in case of AC analysis. You are just looking at one given node and you're plotting your gain response and phase response of your system or of your circuit. And when you say, so for example, when we look at this node called drain, okay, and when I say that the name of this node is drain, I'm explicitly stating the network name, which is selected network, the value in the first single quotes, and not the arc wire. Because here's the thing, if I select this guy, although my network remains the same, the name of this wire, that is the segment that is part of this network, is net@35. So I'm essentially looking at the network name, or as we commonly call it as the node name. So that is it, that is the output node. And once you define this, you will have a gain response in both decibels, like dB power, as well as absolute magnitude. And the phase plot is going to be in degrees. So without delaying any further, I'll enter values to make changes and run this simulation. So the first thing in AC analysis, like always, is I'll be using a vSource from tech_ngSpice library, giving it an initial DC operating point, which is DC is equal to 1, I'll be saying AC is equal to 1 to signify the magnitude of AC signal. Now this is important, like during AC analysis, we would want a finite DC bias point such that this device is operating in saturation region. If so, you are using this device as an amplifier. In this case, this represents the common source amplifier. That's the most default and the universal cell and analog design. So I'm gonna go ahead and VV source @0. And I would like to remind users that the name of the instance is this name. So in this case, I had named it as VN. So I'm gonna make a change here and say VVN. Now the AC start frequency is 0.1, stop frequency is 100 gigs, sweep type decades, and because we need a logarithmic y-axis, and AC sweep points is 20. The parametric sweep device is M1. The parametric sweep device parameter is, in this case, the width of M1. 1 microns, 10 microns with 1 micron increments. And finally, the output node in question is tree. And I can just go ahead and simulate this. So at the end of this, it's going to say that it is writing output underscore all dot raw. And this is where the post-processing tool, collates all these results right under one raw file. And now when I go to trace, insert, I have got, this collated set of results. Now, if we look at this VDB bracket string for a given parameter, which is M1 with 1 microns, VDB signifies the gain response or gain plot in decibels, the power of the gain in terms of power. VM is the absolute magnitude, okay, with respect to your input signal for your gain plot. And VP is the phase response of your phase plot. Now, if I suppose to choose VDB, so I can filter my result as VDB, select one, hit Control A, and say plot. And in order to change the x-axis scale, I can say zoom to all x-axis values and log, hit apply and say okay. The next thing I'm going to do is I'm going to plot my phase. So for that, I can say VP, select all, the same drill. And this time I'm going to say plot in new xplot. So as you can see here, this is the phase in degrees. And this is the phase, this is the magnitude in, the power of your gain response in decibels. And if I want to plot the gain, the absolute, the gain response and absolute magnitude, I can just simply say VM Now, the benefit of this new sweep-based analysis is that if I vary or change the sweep this thing from 10 to 20 microns, and if I had similar, I can simply say Control Shift Insert. Oops. I guess I might have. So the idea was, if I would have said plot all on the existing plot, it would have updated the current SimProbe or the waveform viewer with set of new set points from 11 microns all the way up to 20 microns in all three plots. I'll just have to look back at why is it that it dumped back into a core dump file. So that's dot AC analysis, parametric AC 2D sweeps. The next thing that we have is the transient analysis. So this is the typical test bench for dot transient analysis. And I have explicitly made this test bench to use half graphical user front end, that is signifying the circuit in terms of the cells from tech underscore EFX@035A library and tech underscore ngSpice library. And some users did ask, like, how can we co-simulate with certain conditions as Spice Core? Like, for example, in this case, I have got a voltage source between input and the ground terminal with DC1, AC in terms of a small sinusoidal signal. And the way to define a sinusoidal signal is you have to define the offset. So as you go about giving your empirical equation, which is DC magnitude plus the amplitude times sine of frequency plus the phase, that's the exact same sequence in which you define all these 5 elements. So you have got the offset, then you have got the amplitude of your sinusoidal signal, you've got your frequency, then you've got a delay, and finally you've got the phase that is needed. And this is going to act as my input sinusoidal source as well as to bias this transistor in saturation. I would say just on the onset of saturation. And I've got this dot tran or parametric transient analysis. Now, as you can see here, it goes the same. Instead of the inner loop is replaced by a transient inner loop, which is transient sweep, T start, the starting value if you choose to have the start point of your transient analysis, the stop time, which is in this case is 20 milliseconds, the transient sweep step size. So I would like to add this, that the step size here is the sample space or the sampling in time domain that you are looking for. The Tmax, on the other hand, it's a feature that is going to be added. It's a standard ngSpice Tmax pre-append, but it's a feature that is going to be added. And the initial condition is also a feature wherein if a designer chooses to have an undefined initial condition, that is to ask transient analysis to bypass the initial DC um, operating points and start with uh, the existing node voltages and currents. You can say you can choose or not choose whether or not to have the initial conditions, initial bias conditions. The next thing that we have is the parametric sweep device, which in this case is going to be M1 width. So I'm going to vary the width of M1 from 1 to 10 microns with 1 micron increments. And finally, I have this output field. Now the output field is divided into two sections. The first is the output device, which is which displays the device parameter in transient simulation. So what happens is at every step, if the step size is 10 microns, so at every 100 microseconds intervals, you would be having a dot op analysis running, which would gather the device parameter, which in this case is M1 VDS, and save it in your post-processing result file. And the next field that we have is the output net or iProbe, which is 22 and 23, and the output net or iProbe, which is 24 and 25. So the idea of this is that if you have a given net, which in this case could be, let's say, net at the rate 10, you can mention or define this net at the rate 10 back here, and you can define it whether it's you are probing voltage or the current through iProbe. In case if you are probing current through iProbe, you have to define this as I and replace this field 22 or 24 with the instance name for iProbe in a similar fashion that you might have seen in Dot .opd. So for now, I'm gonna just go ahead and demo the first case, which is output device name M1 VDS, and I'll change the step size from 100 to 10 microseconds, and again, it is going to show you that it's saved in output underscore all.raw, a test wherein that you've reached the end of your simulation. And now when I say insert, I have the VDS of M1 when M1 width is 1 microns all the way up to 9 microns. So I'm just going to go ahead and plot. So as you can see here, for every 10 microsecond intervals, you have your VDS plotted from by performing dot op analysis at every 10 microsecond interval and plotting the device parameter. The second scenario is that you as a designer might, you as a designer might want to probe one of these nets, which in this case is drain, and you might want to probe the current node. So I'm just going to go ahead and plot first the drain node and then the current node at the same time. For this, I'll say drain, and because it's going to be voltage, so it's going to be V of drain. And the next thing I'm going to do is I of V of main. As we discussed earlier, when it comes to iProbe, you need to define it as V of main. or V of the instance name of I probe. And I would like to also add that in order to run the output net and or probe based outputs, you need to pass a pound key or a hash character, like, to the field 18 underscore device underscore name. So when I say insert, I have the probe current, which is the I main. So I'll just go ahead and say I V main. I'm plotting this first because it's in milliamperes and it's a smaller range. And if I choose to append the existing plot, I can say plotted a new X plot. So as you can see, because the drain current and the gate voltage are have a 180-degree phase shift, because so you are essentially seeing a positive current for a negative voltage at the drain terminal. So that's pretty much it for parametric AC sweeps. And once again, I would like to remind that in case if you want to plot the net voltage or probe current, you need to pass a hash character to this field 18 underscore. And as always, the instructions for getting the specific set of outputs is always mentioned out in this output field itself, in the instruction field back here. The next thing that I'm going to demo is dot noise analysis. So the existing dot noise is going to be replaced with a new template, which is dot noise again, but it is refined and it is fine-tuned to rectify certain errors that was shipped out during the beginning of this challenge. And as always, I have this common source amplifier, and then I have this source called VACP, which is nothing but an AC source with a finite DC bias point to bias this transistor in on the onset of saturation. And the noise analysis field has 6 fields. The first is the input source, which is nothing but you have to define the voltage source or the current source that is considered as the input of this circuit. The output node, wherein the noise analysis is going to calculate the output noise and use the gain of this device to calculate the input referred noise. The frequency start, the frequency stop, the sweep type for frequency sweep, as well as sweep points, which in this case I chose to be 100 so that I can get a much of an accurate integrated noise when I'm simulating this. So in this case, my input source is VVACP, which is the input source that you saw back there, an AC source. The output node is my drain node, which is V of drain. And in case if I have a I probe, I can say I of V of drain if I'm looking at the output current. I mean the noise current at the output. And so when I simulate, the first thing that I'm going to see is the input referred integrated noise, which in this case is close to 42 nanovolts, and the output integrated noise, which is 3.67 nanovolts. And I would like to mention this, that this is in, because this is an integrated noise, it is integrating the noise between the start frequency and the stop frequency that is defined in noise analysis. And if I go ahead and plot this, I'm sorry. Okay, there seems to be an error. So since this is currently in development and needs some refinements, I'm just going to go ahead and plot using command line. So I'll say simprobe output.raw. Oops. Yep. So sorry about that. Uh, as you can see, this is still in development phase, but you would expect to see the output noise spectrum and the input noise spectrum, the input referred noise spectrum, between 10 hertz all the way up to 100 megahertz with 100 points per decade. And then you can always use simprobe to calculate or further tighten your integrated noise between specific frequencies using the simprobe calculator. And finally, I would like to also cover the pole zero analysis. And for pole zero analysis, I'm just gonna quickly replace the existing template. And if you see pole zero from the tech_ngSpice library, the node one refers to the input of your the positive terminal of your input source. The node 2 refers to the negative terminal of your input source, and as well as the node 3 refers to the output terminal or the output node, and the node 4 refers to the negative terminal of your output node. So I'll just go ahead and mention these nodes. In this case, I'll mention this guy as in, this as drain, in, ground, and this is going to be voltage. And after you run this, you can go to your run directory, which in this case, since I simulated it on my AC analysis test bench, it's going to be .ac underscore oh, I'm sorry. So it is going to generate two set of raw files, the one named as pole.raw and the other named as uh, which will have your poles in complex now in complex signal values. And the second is the zeros, which will have zeros in your in complex values. And you can always use Octave and read this back using something called as spice underscore read, which we are gonna like add for every user. Like if you start simulating your simulations henceforth, you can also use Octave to post-process your raw files. And that's going to be a feature that's going to be added by the end of day, by today evening, to be pushed to all users. That's pretty much it. But yeah, you can run pole zero analysis and look at your poles and zeros uniquely in these separate raw files. And finally, there's an update to Dot Opd analysis, which some of the users asked for a feature request, since it seems that Dot Opd analysis seems to be crucial for basic bias conditions and for basic DC bias point analysis. So if you now go to Dot Opd analysis and just say name of device as M1 and name of second device as M2 and pass the pound or the hash character to the parameter field of these devices. Now when you run, you'll see three lines. This is an indicator that your simulation is successful. And when you go back to the run directory, .opd example, you'll see CSV files, because some users requested for post-processing these .opd analysis using either GNU Octave or their own Perl scripts. You can use these CSV files So in this case, it's going to use LibreOffice to plot it, and it will plot all the device parameters, that is ID, VGS. So it's divided as uh, the DC or the DC parameters, and then you have your capacitances, towards the end, towards the second half of the spreadsheet. And the first half contains parameters like the various voltages, transconductances, and the currents, you know, at every given node of that active device. So that's pretty much it. And we'll be open up for questions today, since today it's going to be more of a question answer based approach, so that we know that what is it that you as users and designers need or seek to further finish up your designs. So any questions?
Hello.
Hey, Ibrahim. Good morning.
Hi. Good morning. I just have a question that I asked the last webinar, and it was about the noise analysis and the contribution of noise for the different devices. I have seen such simulations before, and I've done it in another software for running the noise analysis, and it gives us the contribution of each
noise. Yeah.
Yes, so that I can fix the problem, or know at least which device is making that such big noise. So could we do something like this in that?
Not at the moment. Not at the moment. So the way I remember is that used to. So I remember back in Cadence, you used to have this instances, that the instance contribution of the noise contribution of each instance, and you can get spot noise, integrated noise. But as far as ngSpice is concerned, not that I'm aware of at the moment, that you can find what's this thing of the individual device.
Okay, in the AC analysis, could I actually, I don't know what kind of operating point the AC is being solved around. I mean, if my circuit is taking time to settle or reach a stable operating point, and they want to do an AC analysis around this point, so it has to wait until it gets the solution at that time, then it uses the operating point at that time in the AC solution. Can we do something like that in here?
Yeah, so are we talking about that ask AC analysis not to, take the existing, what do you call, DC bias points?
I think it takes the DC operating point at the initial run, right? I mean, when you just click run and for the AC analysis, it takes or it solves the circuit at 0 time, and it takes this operating point and solve AC around it, right?
Yeah.
But my circuit, it takes time to settle to a certain operating point, then I want to solve AC or to do AC analysis around this operating point. So how could we do that? In in HSPA or in Eldo, if you know Eldo, we do something like .ob at some time. I mean, we define some time for the circuit to start or to take the operating point at that time, and then solve AC analysis around this operating point.
Yeah, so first you you do .op and then you do .ac, because .op defines the initial bias points of all the, so let's say you have V source, okay, and within V source, if you've said DC is equal to 1.4 volts. Instead of 1, you say 1.4 volts. And when you pre-append it with .op, it's going to first, instead of asking AC analysis to settle down to an operating point, it will read all the existing DC voltages mentioned in your circuit, and then it will start with AC analysis. It won't try to settle down to a stable operating point, because you've already defined by saying .op and mentioning, adding DC sources, or saying that in V source DC is equal to 1.4.
I'm not sure if I got
Okay,
it, but yeah, but I can do operating point at some time. I mean, at 1 micron or 2 micron. So I say .ob space 1 micron, for example. So it will do the operating point at 1 micron. I mean, it will take the operating point of the circuit at 1 micron, not at 0 micron, or just at the beginning of at the very zero time. I mean, initial time.
Okay, so yes, it is doable, but the existing template that we have doesn't support that. So maybe I can just come up with a solution to this specific question. So if I understand correctly, when you said 1 micron, you said you mean 1 microsecond.
Yes, after 1 microseconds, please save this operating point for me, because I'm going to solve around for AC analysis at this operating point after 1 micron.
Okay, all right. Yeah, I believe it is doable, but it's not part of this existing template. But I'll have to definitely look it up and come up with a solution around it. This is in case of circuits where you have some settling time that's needed before you settle down to a stable DC bias condition and
yes,
then run AC. Okay.
And yeah. I think the band gap here, the circuit under test or under a challenge, it has a startup circuit and it takes time to start. So how could we do AC analysis without giving the simulation the information about at which point it's going to solve the AC, at which time? So if my circuit takes time to settle, so I have to put that time to tell the simulator that please wait this certain time, and then take the operating point at that certain time, and then do the AC analysis at that certain time, certain operating point.
Okay.
That's what I'm talking about.
Yeah, I mean, there is no generalized template. I mean, it's better to write a SPICE code, because you're first doing .transient and then you're using a measure statement, and when that condition meets, then you're asking it to perform AC analysis based on the OP saved at that value. So this is the flow. You first do .transient. I mean, you first do .transient, then you use .measure, saying that when a given condition or the settling this thing is reached, when the envelope of that settling reaches 10% of your desired this thing, okay, do a cross, okay, and for that cross you do .op, and that .op is going to save the, and since that point, when you say .op, the next thing you'll be saying is .ac. So it is going to stop this thing, and at that .op point, it's going to run a .ac analysis. Yeah, I mean it is more of a SPICE or ngSPICE code based of a solution rather than a template based solution.
Mm-hmm.
But yeah, I'll have to definitely look into that.
Mm-hmm. I got it. Thank you.
Yeah.
May I ask 2 questions?
Sure.
Good evening or good morning.
Good morning.
First of all, I've noticed that within one of the tutorials inside the knowledge base, the one explaining the most basic inverter cell, when we are making the pins, it is mentioned that we should use bidirectional kind of pin for VDD and ground. While playing around with that, I noticed that besides bidirectional or bidirectional, we have also kinds of pins that actually literally say power and ground. Does it matter? Will it have anything to do with the layout tool? Does it have anything to do with global variables, or is it's just names? Should we name our supply and ground in a special kind of a way, or because this will have cells within cells? So I'm sure will it propagate the way it should, or will it make problems? Will it coincide the way it should when doing the parasitic extraction?
So
that's the and or do you want to answer this one and then listen to the second, or?
No. Go ahead. You can just go ahead with your questions. Yeah.
Okay. And the second question also is concerned with the preview of the layout tool, because while doing the simulations, I was wondering what is actually the step, or maybe to call it a resolution of the of for example the transistor width. So we can make in your email you said that the minimum width is 0.4 microns, but what next? Does it have to be 0.5, 0.6, or can we make it 0.45 or whatever? And then I saw while playing around with the with magic in your preview.efabas.com, saw that one square is 0.05 microns. Can we count on this to say that one transistor is the smallest transistor, the thinnest transistor is 0.4, and then the next one is 0.45 microns, or something else? Thank you.
So I think Tim Edwards would be a better person to ask any layout related questions, and we will be getting him on board in the next webinar. And that's when the actual layout process and the layout this thing is going to begin. And to answer your first question, no, it shouldn't matter, but electric is an all-rounder tool. It also has this layouts aspect tied around it. But since we are not using the layout feature of electric and we are just focusing on the schematic, the reason we ask it to be bidirectional is so that when electric netlists your circuit, okay, in when electric asks this post something called a sim corners, which netlists the electric readable circuit into what you call a spice netlist, ngSpice netlist. That's when all the hierarchy is defined, and that's when we use this bidirectional pin to cram itself up into what do you call this multi-hierarchy set of points. So when you say bidirectional pins, it's a way for sim corners to translate electric's circuit or translate electric defined netlist into ngSpice defined netlist. So, I mean, in a way, it does matter. I'm not sure how power and ground, those explicit pins, affect the hierarchy structure of ngSpice. I haven't tested it so far, but so far, we played around with bidirectional to be readable into a hierarchy element, so that if you have two levels of hierarchy,
that's the way we should go. But just on the same matter, does it matter how we actually call that pin? Can it be does it have to be VDD, or can it be supply or power or?
Okay, so if you are creating a symbol or an icon for this final XBG, what do you call, cell, okay, that's when you have to map it to what is defined in the symbol for XBG035. So I'll just go ahead and clarify it further. Just give me a minute. So yeah, the idea is you want to name your pins to be these guys. You want to map the names of your pins to the icon symbol that is shipped with your this thing.
Okay, thank you.
Yeah.
Okay, great. Just two more comments, if that's okay. Not questions. The first one is concerning your the layout tool. I played around these 2 days, and the tool itself seems quite fine, but I don't know if it's a problem with the preview website. I noticed the connection snaps much more often than the actual eFabless. So
I see.
I don't know if maybe it's my fault. I'm not sure. I just wanted to ask if other users experience the same, or is it with me? But I noticed that it snaps much more often than eFabless. And the second comment is this. I'm coming back to my second question. I understood that you are currently unable to answer, but I just wanted to mention that it's actually also connected to the simulations, not only the layout, because if we create and submit a schematic that includes a transistor which is off grid, then is no good, and the deadline is approaching. So maybe that's a piece of information we should acquire soon. Maybe.
So
if
by off grid, do you mean like it's buried inside a level of hierarchy down, or?
No, I mean like for example, 0.4 is the smallest transistor you can make. And the next one is, for example, it turns out it's 0.5. And in my schematic, I have a transistor which is 0.45 wide.
Okay.
If you see so I shouldn't even try to simulate something which cannot be made in the layout.
Yeah, I mean, the minimum widths are, DRC specific widths or the lengths that are defined. So although it's good when it comes to modeling, or when it comes to these models support going as low as 0.45, and I've seen 0.3 works pretty much all right. But as far as layouts are concerned, like you said, it might be an amazing design on schematic models, but when it comes to layouts, when it comes to these DRC, this thing, it's going to completely violate that 0.4, 0.45. Yeah, I agree onto that. So, but yeah, the email that Tim Edwards sent across, or that that was sent 2 weeks ago with the minimum sizing. Okay, that is something which is to be followed. And so far, we've just mentioned the resistors, I believe, and we have to make sure that we also mention the minimum widths for active devices. Thank you for pointing that out.
Yes, thank you. Thank you. That's all from my side. So,
Alexander? Alexander?
Yes.
Hi, this is Greg. I'd like to ask you just a few questions about your experiences in preview.
Okay.
When you say it snaps, could you be just a little more specific? Do you have the tool open and you're working on the tool?
Not at the moment. Today,
No. When you experience your problems, I just want you to be a little more precise with me about where you see the problem.
Yes. So basically, when I use the actual eFabulous, it happened to me that the connection breaks. I mean, I see that display. I see that desktop, which I see while logging in. That that 30 seconds wait or refresh or something. I see it maybe once a day. With preview eFabulous yesterday and the day before, I saw it like, I don't know, 5, 6, 7, 10 times, something like that. I'm working and then it just stops. I see that display as if I'm just trying to log in.
And to correct it, what do you do?
Refresh.
Okay, thank you very much. We have time for one more quick question if anybody has another question.
Hello?
Hey, Alfredo. Hi.
Hello. Hi. One point here about the layout, the preview. I don't know why, but seems like I have two accounts with the same input, with the same login and things. If I go in the eFabulous site using efabulous.com, I went to an account called Alfredo Coelho. If I use the preview, I go to an account is AR Cartas at the end, LinkedIn, yahoo.com.br, is the email from my EDN links. In the Alfredo Coelho account, I see the schematic, but don't see the layout tools. In the other, using the preview, the AR Cartas account, I don't see the PDK, and I don't see nothing. I cannot use. When I try to use Count layout tool, nothing happens. I don't know. I have two accounts now.
That can happen, Alfredo, if you happen to authenticate. Do you have more than one email with LinkedIn?
No, it's only one.
Okay. So I'm not sure how that happened. Could you, do you have access to the help ticket? When you log into preview, if you create a help ticket and let us know which account you want to be on preview, we'll consolidate those for you.
Well, I prefer the Alfredo Coelho account because I have a lot of schematics there.
Okay, but can I ask you to go ahead and create a tick, go on the website and click that help icon and just let us know which account, describe the two accounts and let us know which one you want to use on preview.
Okay, send a ticket.
Yeah, and I'll be on the lookout for it, and Risto and I will take care of that for you.
Okay. Well, we have no more time for that, seems.
No, we can. If you have more questions, please continue.
A question about the resistors to use in the schematics. I am using the well resistors for this is the biggest resistance for square. But when you send, I receive an email, and there are some definitions about the minimum sizes. I have checked it with XFAB. I have a paper, and they say that the minimum size for the length, the width, almost any width, but the minimum length for the air for the well resistors is 0.7 microns. Sorry, it's 3 microns.
3 microns.
Yes, 3
That's
microns.
right.
But the test that you sent with the width, the 3 microns, or the 15 microns, I didn't understand. Someone is too fast or copy paste. Oh, you
Yeah.
have it here. Oh, okay. Let's see.
So,
Those 7 volts.
so
Capacity.
XPAB mentions that, you know, that you need minimum of 5 squares. Okay. And what they ideally mean is that you need to have a 3 micron square by 3 micron square for a total of 5 squares. That's our recommended size for the resistor. But as far as the size of an individual square is concerned, then it has to be like 3 microns by 3 microns. I mean, that's the recommended this thing versus the limiting.
As my resistor is 3 microns by 60 for this resistance.
Mm-hmm.
That resistance in the near of the bipolar transistors.
Okay.
Where is the DP? Where? Oh boy. One thing I have seen, the minimum dimensions of the the diffusion resistors is 0.7, not 0.5. I don't see, I don't know. Where down, there's something. Well, I'm not using this, only if someone are going to use it, only to be careful about the minimum size. Okay, it's going to be, I'm going now only finish the trimming. Okay. Yes, point. The pin for the trimming, I normally use separate pins for each signal. 3 in 1, 3 in 1, 3 0, 3 in 1, 3 2, 3 3. The schematic, the symbol must be in the digital form is with brackets and 0 to 3 and things like that.
Mm-hmm.
Okay, I'm going to put 10 together because I use it to put separately.
So you mean something like instead of a bus driven input, you want like
I want one by one. I have a lot of trouble with the people put a bus starting to 0 to 3 and the other put the bus starting to 3 to 0. It's a nightmare. Oh boy.
Yeah, you can always do this thing, like once you define a bus, you can say V of square brackets 3, V of square bracket 2. You can vary the voltage of individual lines in this bus by.
Oh, let's see. It's okay. Thank you very much, and let's go. By the way, I have when the errors appear in my screen, I take a screenshot. I use the Linux here. I take a screenshot and send the images to UA. Then you can see exactly what I see.
All right.
Okay, people, thank you very much.
All right. Thank you so much. Yeah.
Let's go for my little schematic. Bye-bye.
Any more questions?
Okay, it looks like that's it. Thank you, Jay. Thank you, everybody, for participating. Is there anything else, Jay?
Nope, nothing. Okay. Anyone else? No, right?
Okay, that concludes this webinar number 4. Thank you, everybody, very much.
Thank you. Yeah.
Thank you all, guys. Thank you very much.